Hi, I'm Alistair, and I made this lie detector machine which you can use in a detective, whodunit, murder mystery escape room game. Let me show you how it works. So here's the machine connected to a maglock that's currently secured. Now if we turn it on, the tape rewinds and then plays back a recording.
This is Detective Lena Marlowe, beginning the interview at 10 o'clock. Did you see Chris at the cafe the morning before the incident?
No, I haven't seen Chris in weeks. I was out of town that morning visiting my sister.
Now players need to decide if that statement is true or false. Now perhaps they find a receipt somewhere else in the room that shows that actually the suspect was in a cafe that morning. And then we hear the next statement.
Can you confirm where you were on the night of July 15th?
I was at the office working late that night. I didn't leave until after midnight.
Now let's say we've got no reason to doubt that statement, we'll say it's true.
Did you speak with anyone after the meeting ended on Friday?
No, I went straight home. I didn't talk to a soul after leaving the office.
Now maybe there are phone records to disprove that, but let's say it's true.
Did you lend your car to anyone the night of the robbery?
No, I don't let anyone drive my car. I didn't even use it myself that night.
Now players know that this is false because there's CCTV footage of the car at a petrol station.
Do you know where Anna might have gone on the night she disappeared?
No, I barely knew Anna. We didn't talk much.
And we also know this is false because there's a social media post of them together at a restaurant.
Interview ended at 10:24.
And once all the statements have been read out, if players have been able to correctly separate the truths from the lies, then the maglock releases, which can open a compartment or a door for them to collect their reward. And if I turn this box around, I can show you the components inside that make this work. So in the centre here, I've got an ESP32 microcontroller that's running all the game logic. Here we've got a motor driver at the top that's powering the two spindle motors. I've got an MP3 module that's playing the audio through this speaker. And then in the middle we've got an ammeter, which is the little gauge that flicks up and down, the toggle switch and the true and false buttons. I should point out that of these, the motors, the motor driver and the ammeter are purely aesthetic optional components. The actual only logic required for the game is to have the true and false buttons and the audio playback. So I've styled this as a lie detector machine, but really you could use the same setup for any kind of audio puzzle or quiz where players hear a series of recordings and then they're prompted to enter the correct response after each one. That can be true or false or a multiple choice. And here's an illustration of how those components are wired together. So I'm using 4 GPIO pins from the ESP32 to the motor driver here, which allows me to drive these 2 DC motors at variable speed, either forwards or backwards. Now I'm just using these cheap yellow hobby motors to simulate the spindles on a tape-to-tape machine, but if I'm totally honest, I'm not 100% satisfied with them. They're quite noisy because they've got just a cheap plastic gear train, and you could either upgrade to use better quality motors or you could just do away with them if you prefer. Here I've got the MP3 audio player, which is triggered by a serial connection from the ESP32. Now it's a DY-SV5W, which I've mentioned in quite a few previous projects, and it's currently my preferred choice as a way to add audio into props. It runs at 5 volts, but accepts 3.3 volt logic on the transmit and receive line to the ESP32, so there's no need for any additional components here. Now you can send commands in your code to trigger playback of specific audio files saved on the SD card. But in addition to the transmit and receive serial lines, I've also connected the busy pin, which is this grey pin at the bottom here, and that's going to go high when an audio file has stopped playing. And that's how the code on the ESP32 will then know to prompt the user for an input. Here I've got a 5 volt relay, which is switching this 12 volt DC power supply to the maglock, and that's going to get released when players have answered all the questions correctly. The toggle switch here starts and stops playback. And then here I've got my true and false input buttons. And these are illuminated buttons, so they each have an LED underneath them. And I'm using warm white LEDs, which give quite a nice glow and a nice aesthetic, I think. Now, these LEDs have got a higher forward voltage than a regular red LED. They have about 2 volt forward voltage and 20 milliamps forward current. So using V equals IR, we can work out the correct value of the series resistor to place in line here. So I'm using 68 ohm resistors to take the 3.3 volt output from the GPIO pins to the correct current limited through the resistor and back through to ground. And finally, I've got the ammeter up here, and much like the motors, this is purely used for decoration. It basically flicks up and down to random values while the audio file is being played based on an analog signal sent from a GPIO pin. Now, that analog value ranges from 0 to 3.3 volts, much like the pins that you use to light the LEDs, but this is a 1 milliamp ammeter. So to make that 3.3 volts correspond to a full deflection of the needle across the meter, we need there to be a total of 3.3 kilo ohms resistance in that circuit. Now, the meter itself already has some internal resistance, so I've placed an additional 2.8 kilo ohm resistor here, and that seems to yield pretty good results. And here is the code that's running on the ESP32. So I'm including an external library, which you can download from this GitHub link here, and this contains the commands that allow us to access and play back specific files from the audio player. Then we have a section of constants. So these define the GPIO pins to which each of the components are connected as per the wiring diagram I just showed you. And then we also have the constants that refer to the audio files that are on the SD card. So every audio file is assigned an index number, and we can play them back by referencing that index number. This is the clip that is played when the game first starts playing, which is an intro sequence. These are the index numbers of all of the audio clips that correspond to a statement that the player has to decide whether it's true or false. And this array at the bottom is the correct answers that players should have to give for each of those statements. So these two arrays will always have the same number of elements. Here I've got 5 questions. The first clip is false, then we've got 2 clips that are true, and then we've got 2 more that are false. And obviously you can edit this to include as many different questions and the correct responses as you want. I've also got an audio file that plays when the game ends or after the last clip has been played. And I've also got a little sample that plays when the players press the input button. Now, originally I actually had different sample sound effects depending on whether they pressed true or false, but I didn't want to give feedback to the players that suggested that the answer they gave was correct or incorrect. So I actually changed that back to just use a constant sample in each case. But if you wanted to, you could change that so that each button gave a different audio sample. Here we declare some globals. So we're declaring a player object, which references the second serial interface on the ESP32. That's how we're going to access the audio playback commands. And then I'm going to create a simple state machine, which describes all the different states that the controller can be in. And we're going to use that in the main program loop to determine at what stage we're at and what status the controller is currently in. So idle is when we first start up, then we're starting up, we're playing the intro, playing clip if we're playing one of the audio questions, waiting for the player input, and these sections here loop round and round for as long as there are questions to be answered, and then we proceed onto the ending state, and finally the game ends. But we start right at the beginning in the idle state. We initially have a score of 0, and we are on the first question, so we initialize both of these indexes to 0. And then we also create a variable to keep track of whether the audio is currently playing back or not. And notice that I declare this as a volatile variable. Now, I have used these in a few projects, but you might not be familiar with them. So Generally speaking, when we declare global variables up here, I'm declaring them as unsigned 8-bit integers, or occasionally we have class instances like we do here. But here I'm declaring a volatile Boolean, and the reason it's volatile is because it can be changed outside of a function in the main program loop. Specifically, it can be changed in an interrupt service routine, which we've got down here. Now, the DY-SV5W has this busy pin that, according to the manual, goes high after playback has ended. And it does, but the problem is you can't simply do a digital read of that busy pin to determine when the audio is played back, because it actually takes a little while, around half a second sometimes, for that to be reset to low after the audio file starts. So if you were to start playback of audio and then immediately start polling the busy pin in a digital read statement in loop to determine it ends, your audio clip would basically end immediately, or your code would think that the audio clip had ended immediately, because it would read the busy pin and get a high signal and go, okay, the audio has ended. Whereas in fact, it hasn't even got round to updating the busy pin that the audio has started yet. So that's a little bit complicated to explain, but what we're going to do is, rather than simply read the value of the busy pin, we're actually going to read when it rises. We're according a rising edge. So when it changes state from low to high, that's when we determine that the audio has stopped playing. And we do that in an interrupt service routine that we're going to attach to a pin. And we don't need to explicitly call that function in loop or anything like that. That will just happen whenever the value of that pin changes as a result of the busy pin having a rising edge. That's when we're going to know the audio has finished playback. So to be able to update the value of this variable outside of the program loop, that's why we need to declare it as volatile here at the top. I have mentioned that a few times in other projects if you want to know more about that. And then we declare a help function called play clip. So this is where we want to play back one of those audio MP3 files saved on the SD card based on their index position here. So we'll say we're playing back the audio, we'll call the play specified method to call that particular index, and we'll update the is audio playing variable to true. Here I've got the setup function. So the setup function gets called once when the ESP32 first receives power, and this is where we do all of our initialization. We'll initialize a serial connection, although this is actually only used for debugging purposes, but I generally include this section at the beginning of all my projects anyway. So we'll just output the file name and the date at which this file was compiled and uploaded to the board. We'll initialize all of our buttons. We'll initialize that busy pin, and we will attach the interrupt routine that I was just talking about here. So what this says is the busy pin that we have attached to the busy line from the audio player to, will get the interrupt that corresponds to that digital pin. We will attach the on audio finished ISR to it, and when the value rises from low to high, we will call this ISR, which we defined up here, and this is what's going to let us know that the audio is finished playing. So like I say, this seems a little bit complicated, but the whole reason for this is because you can't simply do a digital read of the value of the pin at a given point in time. What we want to do is actually a change in the value of that time when it rises. We'll initialize our output pins that we're using to control the relay and the ammeter needle, and our LED pins, and also the motors. Now, because I want to be able to control the speed of the motor, rather than simply setting them up as a digital output that we could write a high or a low value to, I'm going to call the LED setup and LEDC attach pin methods. This is in ESP32 language. This is kind of how you set up an analog output. So you can now write a variable value to it that's going to use PWM to change the voltage at that pin. And that's going to allow us to change the speed of the motor. Rather than simply writing a digital signal as high or low, we're going to write an analog value that's going to create a variable voltage at that pin via PWM, and that's going to change the motor speed. So that's what these extra methods here are doing. We'll start up our instance of the MP3 player object, and we'll set a volume, and we'll specify the pins that we've got it connected to, and that's the end of our setup function. So we'll just output a little debug message here. I've got another helper function here. This simply sets the values of the LEDs to either high or low. So the two LEDs behind the buttons, the true and the false button, we just call this method to set those on or off. I've also got a helper function for the motors. So this one here, the motor driver I'm using, because it's controlling two motors and they can go either forwards or backwards, we would need to specify which motor we want to turn, how fast we want it to turn, and whether we want it forwards or backwards. And the combination of those values here are what leads to the different statements that I've got here. So depending on whether you write 0 to the second channel and the speed to the first channel, or whether you write 0 to the first channel and speed to the second channel, that's going to determine whether it's going forwards or backwards. And obviously how large the value of speed you write, that's going to affect how fast the motor turns. And I've basically defined a couple of presets here. So stop motors is pretty straightforward. For this example, we write a value of 0 to both motors. When both of the GPIO outputs are set to 0, then the motor driver is not going to output any voltage and the motors will stop. For rewind, we want to make the motors turn backwards relatively quickly. So we set the direction to 0 and the speed to 200. And when we play them forwards, well, we change the direction. We're now rotating forwards at a slower speed than when we were rewinding. Now, ideally, I would want them to actually play forwards at a slower speed than this. I tried dropping this down to kind of 64, 50, something like that. But what I found is that the motors often stalled at that lower speed, so they actually stopped moving altogether. At around a value of about 100 is when they would fairly consistently turn forwards, but I actually had to increase them slightly. I've actually put to slightly different numbers for each motor because they weren't turning at the same rate. So I ended up with these values completely empirically to make sure that the motors were always going to turn on at that speed. Like I say, if you use different motors from me, particularly if you used higher quality motors, hopefully you'd be able to get them to turn at a slower speed than I did, in which case you'd need to just reduce this value here. Stop all, so this is when the toggle switch is turned off, as if the machine has had power cut to it. It hasn't actually had power cut to it, but what we're going to do is make all of the outputs stop. So we stop the audio file, we turn the LEDs off, we stop the ammeter from moving, and we also stop all the motors. And then we get on to the main program loop. So the main program loop is going to make use of those different states we defined at the top of the code as to what the controller is doing at the moment. And we go through each section in turn, and the behavior is going to be different depending on what state we're in. But before we get into that, the first thing we want to check is whether the toggle switch, the start button pin, is on or off, because effectively that's going to override any of the logic down here, because whether the machine is currently playing back audio or whether it's waiting for an input or whether it's just been turned on, as soon as that toggle switch is turned off, we want to turn everything off. So we add a section at the top of the code here outside of the switch statement, and this will always get executed. So the toggle switch is turned off, we call that stop all method, and we return to the initial state of the game. Otherwise, we step into the switch statement here. So if the game is currently in the idle state, and this is how we first arrived when we turned it on, what we want to listen for is the toggle switch pressed? If it is, we proceed to the next state, we're starting the game, and we'll initialize all of the variables. So we'll make sure that the relay is locked, we begin at the first question, and the player doesn't currently have any score. We'll rewind the motors for 2 seconds, then we'll stop them, wait half a second, then we'll play them forwards and we'll play the introduction to the game. Now in the example video I showed at the beginning, this is where the detective introduces herself and says that she is beginning the interview. Then we go on to the starting state. Now when we're in the starting state, the intro clip is still playing at the moment. So the first thing we need to do is to wait for that to finish, and that's what we do here. While the audio is still playing, the only thing that's going to happen is periodically we are going to update the value of the ammeter pin to a random number between 0 and 200. So this is just going to make the needle flick around as if it was reading the audio output of the clip that is currently playing. If the intro audio has stopped playing though, so when this is audio playing value has gone high, then what we want to do is we want to begin playing these statements for the player to listen to. So we'll just do a little debug output, we'll turn the LEDs off, we will play the motors forward as if we're playing back audio from the tapes, and we will play the audio clip that corresponds to the current question that the player is up to, and then we'll move forward to the next state in the state machine. That's playing clip. Now, just as before, we need to wait for the audio clip to stop. So in this state here, we were waiting for the intro sequence to stop. Here, we're waiting for the statement to stop. So we'll continue just updating the value of the meter pin while the audio is playing. And as soon as it's stopped, this is where we need to start listening for the user to press some buttons. So we'll stop the meter from moving. We'll turn the LEDs on to indicate that the player needs to provide some input. We'll stop the motors and we'll go on to the next state. While we're waiting for input, what we're going to do is we're going to call the getInput function. Now that's defined at the end of the code here. And this is quite straightforward. It simply reads from the two buttons. If the true button has been pressed, then we'll play the audio clip to indicate that we've accepted the user input. We will turn the other light off. So if the player presses true, what happens is that the false light goes off and the true light stays on, and the reverse happens here. So if you press false, then the false light stays on and the true light goes off. So it's just to indicate to the player visual feedback of what they pressed. We'll just record a little log of which answer they pressed, and then we will wait for the audio sound effect to stop, and we'll return a value to the calling code to indicate which input the player made. So if they press the true button, we'll return a 1 value, and if they pressed the false or the lie button, we'll return a 0. In all other cases, we'll return a -1. Now, if you wanted to add more options, a multiple choice for the player to input here, you could return as many different values as you want. You could have 0, 1, 2, 3, 4, 5, 6, however many buttons you wanted players to be able to choose from. You could return unique codes for each one. -1 is always going to be the special case to say they haven't entered an input yet. And what you'd need to do is at the top of the code, you'd also modify the array of correct answers to say for this question, the correct input that players need to make would have this return value here. Okay. So we check the player input. If it is anything other than -1, that means they have pressed one of the buttons at least. So we'll check whether they pressed the right button. That is in the check answer function, which is here. So we'll simply compare the input value they provided to that value in the array, which I just showed you here. If they choose the correct answer, we'll increase the score. Otherwise, obviously we won't. And we come back up here. We then go on to the next question. And if there are still questions left to ask, so I've hard-coded the value 5 here. What I probably should have done is put that into a variable that you can update based on the number of question clips that you want to play to the player. So I've just hard-coded that as 5, but if you want to ask 10 or 20 questions, you could just update that value there. And for as long as there are still audio samples to play, we turn the LEDs off again. We play the motors so it looks like the tape is advancing again. We're playing the next audio clip, and we'll just put some debug output. We will play the next audio file because we've increased the value of current question here, so we're now playing the next one. And then we go back to the playing clip state. And we keep on going back between playing clip, waiting input, playing clip, waiting input, playing clip. We keep doing that until the value of the current question counter has exceeded the total number of questions that we are going to ask. Now when that is the case, we fall into this statement block here. So we turn the LEDs off and we've reached the end of the game. Now here I'm printing this out for debug information, but what happens as far as the player is concerned is that they hear the outro clip. So this is the concluding the end of the interview. And then we move on to the ending state, waits for the audio to stop playing, stops the motors completely, and then we write a value to the relay pin depending on the value of the score that the player achieved. Now, this could be a requirement for players to answer all statements correctly, or you could say so long as they answer more than 80% correctly, or 9 out of 10, however many you want, you can update this value here to implement different logic. And so long as this condition is met, so long as score is greater than 4 in my case, we're going to write a low value to the relay. That's going to cause the maglock to release and the door will open, or players can access whatever they want. In all other cases, the relay pin will stay high, the maglock will stay energized. And now if you want to reset the game to play it again from the beginning, all you simply need to do is to toggle the start lever off and back on again, and it starts all the way from the beginning. All of the game state is reset and you can play it through again. Now, as I mentioned towards the start of this video, this doesn't have to be a lie detector. You could use this same circuit and the code to create any kind of game where players hear an audio recording and then have to select the correct response. So you could play them samples of different bird song and they have to identify what bird made that noise, or ask them a riddle, or any kind of multiple choice quiz question. The reason I went for the lie detector is because I like the idea of acting like a detective, to have to identify that piece of evidence that contradicts the witness statement, and then that whole logical deductive process of separating the truths from the lies. It's like being in a murder mystery or a whodunnit, or if you've ever played the Phoenix Wright Ace Attorney games, it's a lot like that, and I just think it's a lot of fun. Now, as always, I will be uploading the code and the wiring diagram over to my Patreon account, where you can also find all the resources to go with all my other escape room projects on this channel, and I'll put a link to that below. I've also recently set up a Discord server, so if you'd like to ask me any questions or to chat to other people who are making this project and my other escape room projects, you can also head over there and join the server. It would be great to see you there. Otherwise, you can always leave comments and suggestions under the video here, and I'll do my best to read them and get back to you. And I just want to say thank you all very much for watching, and I look forward to seeing you next time. Okay, cheers, bye.